Thanks, everyone. And John, thanks a lot for that introduction. I can't imagine a worse and more frightening way to do a talk than to be the speaker right after Josh. So please lower your expectations. But let's talk a little bit IPython in the context of a tool that we hope to make it, okay, let me time myself, that we hope to make a very good tool for managing the entire life cycle of a scientific idea. And so what I have here is a very toy, cartoonish version of the kind of flow, the mental flow and the process of scientific work, which tends to, we would like to be something where we start playing with an idea, perhaps a data set, perhaps some algorithms that we have in mind. These days, typically, if any idea is going to pan out, it involves collaborating with colleagues in one form or another. If things really start looking promising, most production work tends to be large-scale, tends to involve large-scale computing these days. Hopefully, as Josh was saying, at some point you do paper.submit to journal equals science, and hopefully with results that are reproducible. And eventually your results are not retracted 6 months later, so they actually become part of the canon in your field, and they teach the next generation of scientists, and we keep cycling on that flow. And unfortunately, most of the machinery that we have for this kind of work today imposes very unpleasant barriers between each of these steps. We tend to have to change tools and switch gears, which means that the flow tends to be only forward. You can never go back. It's difficult to iterate. It's difficult to reproduce. It's difficult to be flexible and sort of consistent. I want to present IPython, which is something that started just basically, as John mentioned, as an interactive shell, as a tool that tries to provide fluid transitions across this workflow and tries to sort of let you be the space in which you manage kind of this your scientific thinking. And I'm going to try to do that with a couple of demos. So the IPython notebook is something that started, as John mentioned, that we wrote basically as a way, following inspiration from Mathematica, which is really the system that blazed the trail on this, as a way of keeping together code, figures, documentation, and everything into one single environment so that we could basically have the modern version, the computational version of a traditional laboratory notebook or mathematician's kind of scratch pad. And so the notebook is a web-based environment in which you can type all of the Python code that you would type at a Python prompt, but you do so in cells, and the outputs that those cells produce is saved immediately there. So for example, in here, a very simple plot from matplotlib goes immediately into a cell. We try to make common tasks easy. So for example, if you have to grab a chunk of code from somewhere else, such as the official Python tutorial, and you simply paste it, it will still run because we strip those input prompts and all that. We try to give you informative ways of looking at error messages in everyday workflow. You try to run a script that doesn't exist. We highlight things. We highlight tracebacks. We let you document, as I said, what you're doing. So you can type not only code, but text. And this is text that using Markdown, which is a very simple way of producing markup that allows you to do basically anything that HTML can do can be done in Markdown, including snippets of source code in other languages. Importantly, for a community such as ours, you can include mathematical text, and it's rendered correctly thanks to the fantastic MathJax library, which is an effort funded jointly by the American Mathematical Society and the American Institute of Physics to provide a JavaScript implementation of LaTeX effectively. But now, because we are working in a browser and because we were so slow to get this finally functioning, as John mentioned, it took us years to get it, our platform is a browser, means that we get for free everything that a browser can show. So you can include not only, as you work, plots and figures that are produced by your outputs, but now you can have the notion of objects whose representations, Python objects whose representations themselves are anything that a browser can show. So for example, in here, this is not calling matplotlib to plot something. This is, as you see, the out prompt in there indicates that this is a Python result. And it's a result whose representations happens to be graphical. So what we've done is we've extended the notion of the wrapper of a Python object from being a string to being an entire protocol, such that objects can provide other richer form representations of themselves. In this case, an object can provide image objects can provide graphical representations of themselves either as bitmaps or as vector images, but not just static images. Since we are working in browsers, we have video, so we have an object called a YouTube video, to which you pass simply the hash identifier for that video, and its representation will be an embedded video frame, which actually does play. If you click on it, the video will pull from YouTube and it will play. I'm not going to make you listen to a 1-hour talk, but the point is, now this is part of the document where you have math, you have code, you have results, you can have instructional materials, and all of it goes into one, can be kept into a single environment. Entire websites can be embedded, so you can link other resources, and this is actually the live Wikipedia mobile page, which embeds nicely. So if I search for SciPy, that's what the Wikipedia page for SciPy is. And incidentally, this is actually a screenshot of an old IPython session in matplotlib that is on the main, it's a screenshot that is on the Wikipedia page for SciPy. You can load remote codes very easily. All of us, when we're working with matplotlib, what we tend to do to get a plot working is to go to the matplotlib gallery, scan visually for something that looks vaguely like what we're after. We click on it. This sounds interesting, and you could copy and paste. But matplotlib provides a direct link to the source code, which is right here. So if you copy that link and simply type load, IPython, assuming SourceForge is up, which is always a tricky proposition. This may or may not work. Well, it is up. IPython will load that code straight from SourceForge, and then you can simply execute it. And you have your example right there, which makes it very easy to begin playing, modifying with it until you get exactly the code you want. And if you're working on a bigger monitor than this, you can just drag and drop the source link, and it'll get loaded. So we basically try to give you something that really provides sort of all the pieces for the entire set of machinery that everyday scientific work includes. And since many of our results in science require mathematical representations, we've added, just like we've added image forms or video forms of output, there's a notion of a LaTeX representation for an object. So you can have not only type math in the text areas, but objects can represent themselves as mathematics. So in this case, using LaTeX syntax, and that plays very, very nicely with the SymPy package, because it means that by loading an extension that basically wires this machinery automatically into SymPy, whenever you compute anything with SymPy, the results are nicely rendered in properly displayed math form. So as you use SymPy for everyday work, you're actually reading mathematics, and you're not reading just ASCII art. Furthermore, because as Josh was saying, Python is super glue, we've built into the system the ability to talk to other systems. In particular, I'm going to illustrate it with R, but Stefan recently, modeling after what I'm going to show, wrote an exact analog of this to also talk to Octave. So if you load an extension that we provide, you can talk to R. I'm going to provide a very simple example. Let's suppose that you have a little data set, which obviously you could do some modeling with Python, but for some reason you want to use the R code to do a linear fit on that little data set. If you put $%R at the top of your cell, then right here you can simply copy and paste R code, and when you execute this cell, it will call to R, and all of the outputs, including figures from R, will be kept right in there. Furthermore, you were able to tell it that you want the X and Y variables that you had in Python to be visible to R, and that they will be passed automatically, and that when it finishes, the variable XY coef that was generated by R is available to you as a Python variable. So it makes it very, very easy to basically drop the pieces of R that you need, or Octave, into your regular workflow. Same thing with Cython. We had a lot of discussions yesterday about performance and how Cython is one of the tools that we can access, that we use in Python to speed up our workflows. So a very simple example taken from their documentation, if you write the most simple-minded numerical integrator that you can think, if you run this in Python, it won't be too fast, and if this happens to be performance critical for you, Cython makes it fairly easy to speed it up by adding a couple of type declarations. But now in the notebook, all you have to do is put $Cython at the top. You can paste the Cython code in there. It will automatically compile it, cache it, and load it into your namespace. And then when you run, you can now run a timing comparison, and you'll see a factor of, I don't know, roughly 80 or 90 speed up just by adding a couple of type declarations right in the same space. So we basically try to make that process as seamless as possible. 10 minutes, okay. Once you, as I was saying, once you go from being, from having an idea that seems to work for you, at some point you will want to collaborate. And one of the ways in which you can collaborate these days is on the internet. So someone out there recently wrote this little app on the Google App Engine called Notebook Cloud, which allows you to log in with your Amazon credentials and your Google account into this particular panel, and lets you start an Amazon instance. It will launch it for you, and it'll take, I'm not going to wait for it to launch because basically it will give us exactly the same notebook screen that I had, but this will be now running on Amazon. You log into it, and you'll be logging into an instance of a virtual machine that has all of the scientific Python libraries preloaded for you and a notebook ready to start. And when you're done with it, you can shut it down. You decide which type of instance, how powerful do you want it to be, so you can do your testing on a micro one, which is very cheap and free for the first year, and then start again the same thing on one of their on one of their Death Star ones that cost $2.50 an hour, but that are very fast. And you'll be running the exact same code because it's the same exact AMI, simply running on a different type of hardware specification from Amazon. Okay, so right now it's booting. This link eventually will turn into serving, and it'll become a link. You click on it and you log into it. So that. Once you can, once it's running there, you can invite a colleague, and the two of you can be working in the same notebook, collaborating and doing your work with something akin to, say, Google Docs, but with the actual execution of code. We don't have real-time synchronization, but the basic idea does work. And this leads us to the notion, now that we can freeze, dovetailing into what Josh was saying and one of the questions about reproducibility, now that we can freeze on Amazon and put up there an entire image that has all the code and all the data related to a paper, it leads us to the possibility of truly reproducible computational work. Titus Brown, who is very well known in the Python community and the scientific Python community, beat us to the punch with the first paper that came out as an Amazon Python AMI glued together with an IPython notebook with this paper. On genomic analysis, and if you are interested in it, you can click in here and you will get the Git repo for the data, the link to the Amazon image, and the IPython notebooks to execute the code. A few weeks after that, at a workshop in Boulder, we did the exact same thing, and with some colleagues from CU Boulder. And what we did was simply put up in here the information to configure a project from MIT called Star Cluster by the fantastic Justin Riley that allows you to deploy not only one Amazon AMI, but an entire cluster of Amazon AMIs that boot up as an IPython cluster with the head node already running as an IPython notebook. And so anyone who wants to reproduce the results of this particular paper, all they have to do is copy that bit into their Star Cluster configuration, type Star Cluster start, they will pay for the run, and they will be executing the paper. So I think we do have finally a way of actually saying, if you don't believe what I ran, run it yourself, tweak the parameters, and see what you get. And finally, at some point you will want to hopefully publish something. So this is an example of a notebook that I wrote recently as a chapter for a book introducing just the generic Python ecosystem. the scientific Python ecosystem. So there's text, there's links, there's some math, there's some plots, kind of exactly the kinds of things that I was showing you a minute ago. But what I want to show you is that from this notebook, we can go to this PDF produced by PDF LaTeX automatically. So there's not a single line of hand editing. This is strictly converted from the notebook, from the IPyNB file, running a converter, produces the text that then gets compiled into this with blocks, with code, with figures, etc. So we have a way. So hopefully the code, those of you who burst into spontaneous applause, I would love to see you at the sprints, because the code that does this hasn't been merged into IPython yet, because I've been just hacking it on the weekends as I need to get it working. But we really want this code to be finished, and I'm going to try to get it finished this weekend during the sprints. It's one of our priorities. So if anyone here is interested in helping with that, please, time 5, thanks. It'll be perfect. Please give us a hand. It's easy code. You don't have to know anything about IPython. It's pure document formatting. It's decoupled from the machinery of IPython, and it is very high value. It's something that we all really, really need, because the same code converts notebooks to restructured text, Markdown, HTML, LaTeX, PDF, etc. So hopefully those demos do go to kind of the idea that IPython provides an environment for managing this workflow. Importantly, the notebook format that produced that PDF file that I showed you is an important part of this entire puzzle, and it's something where we want your feedback. The format is very version control friendly. It's JSON. It's made to be easy to machine process, but human fixable. If you need to fix something in there, you can edit it, and this is critically important. There's lots of hooks in there to annotate with metadata what you're working, so that you can do other kinds of analysis in the future about it. And we really would like this to become the format in which we exchange computational work. So please give us feedback. Let us know what is or isn't a good idea there, because we would like this to become something important. And up until now, I've shown the notebook, which is really something that does have us all very excited. But for us, it's important to keep in mind that the notebook is just the tip of a spear whose body is really, really big. The body of that spear is 10 years of work on the IPython infrastructure, which is a design for interactive and distributed computing around Python and I don't have time to go into the details, but the point is that this architecture lets us offer not only something like the notebook. In fact, the notebook itself is a very small fraction of the total code. It lets us offer the classic shells that you've seen before, modern shells based on the Qt toolkit that have the feel of a terminal, but provide a richer, more modern environment, including syntax highlighting and plots. The notebook that you just saw, these are clients that we provide, a parallel computing architecture that unfortunately I don't have time to go into, but that Josh also mentioned briefly. We did talk about this in detail at the tutorial. But furthermore, because all these things are kind of documented and have a reasonably solid architecture, there's an external ecosystem that is growing around this. So Microsoft now has a plugin that provides an IPython shell for Visual Studio. A Berkeley student wrote a Vim client that controls an IPython kernel from within Vim. Microsoft is now supporting, in their kind of reboot of the Azure platform, the deployment of notebooks on their platform. Star Cluster, the project that I mentioned to you guys, gives you basically a single config file way of, with one command, deploying clusters on EC2. The notebook cloud, this notebook cloud app that I showed you was also written by someone external to us with just minimal feedback on the list. Enthought now has something new coming out in EPD8 called Canopy, which is a modern development environment that includes the IPython console in here. In fact, the development of the Qt console was funded by them, and all of that work with the Qt console was done by Enthought for this project. But we benefited from that by using that support for building the architecture. Somebody even built an Emacs client for the notebook. So if you don't like to work in a browser, you can work with an Emacs with the notebook. And somebody just recently, a few days ago, built a new application that lets you work with the notebook but have the rendered views and the slide views on the side. I haven't even had a chance to test this. Obviously, to wrap this up, as you can imagine, this is not my work. This is the work of a large body of people. Those who are boldface are our core committers. The blue people are here in the room. And at the top I've highlighted Brian Granger, who unfortunately could not make it, but who's been kind of my partner in crime in this project for a long time, along with Min, who was a student of Brian's initially and is now at Berkeley and is really kind of our secret weapon in this entire project. But Brian unfortunately couldn't make it, but it's really important to highlight the contributions that he has made. And also the support that we've received from Nthought, from Microsoft. We do have some funding right now from the DoD, but we have never had much stable support for IPython, and we do really need it. If you have ideas on how to improve the situation, please talk to me, because it's proven to be remarkably hard to convince the federal funding agencies that this is worth anything. And we just don't have the resources to sort of continue working on it in a systematic way. And I'm going to leave this up because I know that the timing is tight. There was a question about reproducibility, and so this is just a quick plug for a workshop that we're co-organizing with Randy Levesque and William Stein and others that will take place at Brown in December at ICERM on reproducibility in computational mathematics. Funding agencies will participate, industry will participate, and a bunch of academic researchers. So those of you who are interested in that topic, please have a look at this. The URL is up there, and come over. It should be an interesting discussion. Thank you very much.
Take a couple of questions.